In a rare cosmic discovery, scientists have detected an interstellar object, 3I Atlas, releasing water vapor while still far from the Sun, a phenomenon that has left astronomers astonished. Using NASA's Neil Gehrels Swift Observatory, researchers identified ultraviolet signatures of hydroxyl, OH, a byproduct of water molecules broken apart by sunlight. What makes this extraordinary is that 3I Atlas was nearly 3 times farther from the Sun than Earth when it began spewing water, a region typically too cold for ice to sublimate. NASA researchers say this level of activity is unlike anything ever recorded from an interstellar object. Lead researcher Zixi Xing and the team behind the discovery emphasize that each interstellar visitor reshapes our understanding of how planetary systems evolve. Every interstellar comet we study tells a different story, Xing explained, noting that Atlas's distant water activity could rewrite existing cometary models. When we detect water, or even its faint ultraviolet echo, OH, from an interstellar comet, we're reading a note from another planetary system, study co-author Dennis Bodowitz, a professor of physics at Auburn University in Alabama, said in a statement. When the Swift satellite turned its ultraviolet eye toward Atlas, it saw something astonishing: hydroxyl emissions, telltale signatures of water molecules that have broken apart by sunlight. But the catch, Atlas was still at 2.9 astronomical units from the Sun, well outside the zone where normal comets begin to boil off water. The measured rate was startling, approximately 40 kilograms of water per second, equivalent to a fire hydrant blasting at maximum pressure, water gushing from an object that should still be frigid and inert. To sustain that level of output, standard comet models would demand that a substantial portion, perhaps 8% of the sunlit surface, be actively sublimating. But on a body perhaps 5 to 6 kilometers across, that's a vast area. And yet the water signal is not tightly clustered. It spills outward, diffusing into a cloud of icy grains in the coma, as though each fragment were a microjet of steam. In other words, some of the water is not coming directly from the nucleus, but from fragmented ice grains suspended around it. The distributed sources augment and blur the signal. Still, the sheer scale of outgassing strains the limits of conventional theory. What internal process, what layering of ice, what structural quirks allow this to happen so far from the Sun? If water was the headline, carbon dioxide, CO2, has become the twist in the plot. JWST's infrared spectrographer recorded a coma dominated by CO2 in a ratio of about 8:1, CO2 to H2O, the highest CO2 dominance ever measured in any comet. One interpretation, the nucleus is intrinsically CO2-rich. Perhaps Atlas formed near or within the carbon dioxide ice line of its parent protoplanetary system, where CO2 could condense reliably. Or perhaps its exposure to cosmic radiation over eons altered its outer layers, driving off water and leaving CO2 to dominate. Another possibility, the interior might be insulated, preventing heat from penetrating deeply. Water may lie deeper and be harder to liberate, whereas CO2, less volatile but more mobile under certain conditions, can escape more readily. Or the very structure of the nucleus may promote CO2 venting while suppressing water flow. Additional compounds, carbon monoxide, CO, carbonyl sulfide, OCS, even metallic elements like nickel have also been detected in trace amounts, layering further complexity onto the chemical portrait. This is no ordinary comet. It is chemically exotic. Its makeup suggests a history far different from anything created inside our solar system. Since its discovery in July, scientists have been using various telescopes to learn all they can about 3I ATLS. Their findings so far indicate that the comet is zooming through our solar system at speeds in excess of 130,000 miles per hour, or 210,000 kilometers per hour, in an unusually flat and straight trajectory. In many ways, 3I ATLS behaves like a traditional comet. It has a coma, ejects gas and dust, grows a tail, experiences non-gravitational forces from outgassing. But the details, the proportions, the spatial patterns, the timing, speak of something more peculiar. The CO2 envelope spreads broadly, as though it flows from a subsurface reservoir or porous matrix across vast swaths of the nucleus. The water eruptions, by contrast, seem localized, perhaps tied to vents, fissures, or icy grains drifting in the coma itself. The two volatiles may emerge from entirely different regimes within the object, one gently seeping, the other explosively bursting. And then there is the dust. The coma shows signs of icy grains, microscopic fragments that act like countless mini steam engines. These grains, if they break apart under sunlight, could release water far from the nucleus, contributing to that broad, diffuse water signature. In effect, the coma becomes both source and mediator of activity. Photos show a tail forming, lit faintly by sunlight, stretching outward into darkness. But its structure may not be symmetric or simple. Jets, dust plumes, irregular ejection may sculpt complex patterns. From afar, the nucleus remains a compact point, unresolved, invisible behind its own veil of gas and dust, but with each observation, the veil adjusts, warps, flickers. Something shifts inside. As Atlas plunges deeper into the sun's gravity well, the stakes rise. Its closest approach, perihelion, is predicted near the end of October 2025 at about 1.36 AU. Curiously, at that moment, the comet will be behind the sun from Earth's vantage point, hidden, unreachable by ground observations. In effect, we lose direct view during its moment of greatest heating, greatest stress, greatest potential for transformation or destruction. That blackout window is a cosmic tease. What might happen behind the curtain? The comet could fragment, erupt violently, reorganize, or simply pass through quietly into the outer reaches. All that drama might unfold unseen. Spacecraft, however, might peek in. Missions around Mars or interplanetary probes like ESA's JUICE might record glimpses or spectral signatures when Earthbound telescopes cannot. Once Atlas emerges from conjunction, astronomers will re-engage, tracking its tail, monitoring brightness, looking for unexpected accelerations, fragmentation, anything that signals a turning point. Will it behave like all comets do, fading, settling, walking away? Or will new anomalies emerge? The next few months may hold the answer. Amid the data and spectra, provocateurs speak boldly. Could Atlas be more than a comet? Some have floated the idea of a technological artifact, a probe, or a vessel camouflaged by cometary disguise. The pathing, the blackouts, the chemical oddities, all are fodder for speculation. In one hypothesis, a burn maneuver behind the sun could stealthily launch a payload outward. But such theories demand evidence, and so far, none has risen above rumor. More conservatively, Atlas may simply be a highly processed, unusual comet, shaped by cosmic rays, by ejecta-stripping, by extreme aging. Its interior may be stratified, with volatile-rich pockets and dead, inert crusts. Over eons in interstellar space, sublimation, radiation, and microcollisions could have sculpted it into a shell hiding exotic reservoirs. One scenario, in its parental system, Atlas formed near the CO2 ice line. Over billions of years, water ices closer to its interior were lost or compressed. CO2 became more dominant. When it was ejected into interstellar space and drifted for eons, surface layers eroded. Cosmic rays may have altered composition. Now, as it returns toward a star, the conditions trigger the release of CO2 broadly, while water escapes only via cracks, fractures, and embedded grains. Alternatively, a layered structure could shelter water deeper inside, requiring particular stress thresholds, thermal pulses, crack propagation, to release. The outbursts may shift as it warms, revealing new active zones. Still, none of this fully squares with a continuous 40 kilograms per second water output at 2.9 AU. The standard models strain. The comet is pushing the edges of what we call comet physics. As Atlas sweeps closer, astronomers and amateurs will monitor for several key signals. Each could break open the mystery. Brightness surges. Sudden jumps may signal new vents opening or fragmentation. Tail morphology changes. The tail might twist, split, or warp depending on jet activity and solar wind. Non-gravitational acceleration. Deviations from predicted trajectory may hint at asymmetrical outgassing or hidden jets. Fragmentation. The nucleus might shed chunks, creating multiple bodies or a dust cloud. Spectral shifts. The ratio of CO2, H2O, CO, OCS, metallic signatures may evolve as new layers are exposed. Infrared or thermal anomalies. Unexpected thermal profiles could betray internal heat, latent reactions, or localized warming. Unexpected object release. Tiny fragments or even artificial structures, if present, might depart from the nucleus at odd velocities. If nothing unusual happens, the natural comet hypothesis survives. But if something does go sideways, the story may change drastically. Why does Atlas matter so much? Because it's a messenger from another star. Every molecule in its coma, every dust grain carries memory, a record of a distant protoplanetary disk, ancient radiation fields, stellar nurseries far beyond our sun's domain. In Oumuamua and Borisov, we glimpsed the diversity of extrasolar wanderers, one asteroid-like, one comet-like. Atlas is rewriting the script again, with chemistry that challenges known comet families and a behavior we struggle to simulate. If Atlas is typical of more interstellar comets, then our understanding of planetary system formation must widen. If it's rare, it becomes a treasure, one of the few probes we'll ever get of other planetary systems. Even the speculation of something artificial, while unlikely, invites us to ask deeper questions. How would we detect a non-natural visitor? What signatures would betray technology masquerading as ice and dust? Atlas becomes a test case, a calibration for our cosmic vigilance. Picture Atlas drifting for eons through the cold void, unloved and unseen, until gravity or chance nudges it into a new trajectory. It falls into our system, first a whisper, then a roar. Around 2.9 AU, where comets of our system sleep, Atlas is wide awake, disgorging water, launching icy grains, feeding a glowing coma. Telescopes detect OH in the ultraviolet, read its flows, parse its emissions. Atmospheres dare not hide it. Deeper in, JWST reveals a CO2-rich halo. SphereX, Hubble, ground telescopes confirm dust composition, isotope hints, metallic traces. Mars orbiters plan to catch glimpses when it passes near, gaining angles Earth cannot. Then, as it draws near to the Sun, Earth observations fade into blackout. The grand show plays behind the solar glare. We wait, we speculate, we hope instruments in Mars orbit or out in deep space will peek at the action. When Atlas re-emerges, we may look not at the same comet, but a transformed one. Time will tell. Will it survive the heat? Will it fragment? Will the CO2 dominance wane or grow? Will water bursts intensify? Will the unexpected happen? We stand on the verge of revelation. 3I Atlas is neither fully familiar nor wholly alien. It is a bridge between the known and the unknown, a comet promising to stretch the definitions of cometary physics, planetary system chemistry, and interstellar archaeology. Soon, the blackout will end. Telescopes will resume their vigil. Data will pour. Some theories will be confirmed, others burned away. And perhaps, in the fluctuations of its tail, or the abrupt flash of a burst, we will glimpse something we never knew to expect. For now, Atlas drifts through the solar system like a smoky enigma, with steam, ice, CO2, dust, and maybe secrets too subtle for us yet to catch. But we are watching, we wait, we listen. The comet's journey becomes our invitation to wonder.